we are going to talk about the Gaussian mixture model. Okay, so the Gaussian mixture model. Okay. Now, I showed you the Poisson windows, which puts a bump on every data point. That's kind of like the non-parametric RBF. So Poisson windows. Okay, so there's a bump on each data point. That's analogous to the non-parametric RBF. Okay, and so the Gaussian mixture model basically is analogous to the parametric RBF network. So parametric RBF network. And so instead of putting a bump on each data point, you fix a number k, the number of bumps, and you put the bumps at k bump centers. Okay, so a bump on each of k bump centers. Okay, and that's the Gaussian mixture model, which we typically abbreviate to GMM. Okay, so this is the GMM, the Gaussian mixture model. Okay, now let me illustrate with a bunch of data points. So imagine you have a bunch of data points. Okay, and you might decide that you're going to model this with 4 clusters or 4 centers. So you might place 4 centers, okay, at different points. Okay, those are my 4 centers. So you have k centers in general. So the center positions will be vectors mu1, mu2, mu3 up to mu k. So think of these as the bump centers. Okay, and now these bumps each have a shape. Okay, now spherical bumps would be spherical or circles in 2 dimensions, but we are going to allow the bumps to have a more general shape. Okay, so for example, this bump might have this shape. So okay, and this bump might have that shape, and this bump might have that shape, and this bump might have this shape. Okay, so you can think of the shape as being specified by sort of a rotation, an angle. Okay, and then a major and a minor axis. Okay, and so those are that shape is specified by what we call the covariance matrix of the bump. Okay, so you'll have shape parameters sigma 1, sigma 2, sigma 3, sigma k. Okay, these are the bump shapes. Okay. And you could also imagine that, we get to specify the bump weights. So how much of the data sits under each bump. So we might think of, bump weights, W1, W2, W3, and so on up to WK. These are bump weights. Or how much data, proportionately speaking, relatively speaking, how much data sits under each bump. Okay, when I say sits, of course, that's metaphorically. Okay, and so that's the basic idea. So we get to pick, so we're going to model this data, we're going to try to extract the density, the probability density models the data. In other words, you could think of it as having generated the data. Okay, so we're going to model this data by picking k bump centers, okay, k shapes, okay, and the weights of each bump. Okay, and once we have picked these, we have the density. Okay, and so the probability density p hat of x. So our estimate p hat of x, let's call it p hat because it's not p. P is the true. Okay, p hat of x is going to equal the sum over all our bumps. So this is, now you place the bump at over each center, and if you're at some other random point x, okay, you take the contribution from each bump and add. So it's the sum from little k equals 1 to big K of the weight of the bump k, WK, and the formula for the bump, the probability density that corresponds to the bump. So we'll call that n of x. Okay, and this distribution, okay, this density for a bump, n of x, okay, will typically depend on the bump centers. Okay, it'll depend on mu k, and it'll depend on sigma k, its shape. So it'll depend on its center and its shape, sigma k. Okay, and so this is the form. This is a general. You can think of this as a general formula that computes a probability density as what's called a mixture, a weighted mixture of bump densities. Okay, where in our case the bump densities depend on the center of the bump and the shape of the bump. Okay, and so let me tell you the kind of bump that corresponds to the Gaussian mixture model. It's basically that this bump is a Gaussian density. So n of x, the Gaussian density, given the center mu k and the let me call it just mu now. So given the center parameter and the shape parameter. So now when we're talking about the Gaussian, this is typically called the mean. Okay, and this is typically called the covariance matrix, and indeed for a very good reason, because if you generated data from this Gaussian, the expected data point, the average value, which is a vector valued average, the average data point will indeed be the mean, and the covariance matrix of the data will indeed be this parameter sigma, the covariance matrix. Okay, so the Gaussian distribution is given by 1 over 2 pi to the d over 2. Okay, so in some, I'm giving you the general version, which is in some arbitrary dimension d. The determinant of sigma, so this is the notation for the determinant of sigma to the 1/2. Okay, then we have the exponential, the Gaussian e to the minus 1/2 x minus mu transpose sigma inverse x minus mu. Okay, so this is the Gaussian density. And I'll tell you some facts about the Gaussian density. If you generated a lot of data using the Gaussian density, and then looked at the average data point. So if you generated data x1, x2, x3, and so on up to x, let's call it m. Okay, then the average or the sum, so the expected data point, so the sum of xi 1 over m, this converges to the expected data point, so the expected value of x, okay, which is mu. So the center is not only the center of where we place the bump, but it also happens to be the average data point if you were to generate. Okay, and it also turns out that if you compute the average of the outer products, so 1 over m, the sum of xi transpose. So this is a d-dimensional vector. This is d by 1. This is 1 by d. So this is a d by d matrix, and you're taking the average of d by d matrices. This converges to the expected value of xx transpose, which is mu transpose plus sigma. Okay, so these are just facts. So you can go and perform the integrations that correspond to these expectations and derive this, or look in a textbook. Your pick. Okay, but these are facts about the Gaussian distribution. So it's very nice that the center parameter corresponds to the average data point, and the shape parameter corresponds to the covariance matrix of the data. If you take this guy and subtract mu transpose, you get exactly the covariance matrix. Okay, so. Okay. Now, in order to interpret this as a weighted, sum of bumps, we typically want that the wk are greater equal to 0, and the sum of the wk is equal to 1. So it's a k equals 1 to big K. So this is a weighted sum of bump densities. Think of this as a weighted sum of bump densities. Okay, so this is the basic idea. The basic idea is that we have a mixture density that we're trying to fit to the data. It corresponds to placing the centers at clusters of the data and choosing the shapes of each bump, and also choosing the weight of each bump. How much data is inside that bump? Okay, and what do we get to do? We get to pick all these parameters. So we will pick all these parameters so that we sort of match the data. So we get to pick Okay, so we get to pick the centers, okay, the shapes, and the weights. So we get to pick the weights, Wj, the centers, μj, and the shapes, sigma j, for j equals 1 to big K. Okay, so we get to. So how should we pick them? Well, we should somehow pick these parameters that we get to pick in order to fit the data. Okay, so we saw this before. A very common approach is to use the method of maximum likelihood. So since this is a density, it is explicitly quantifying the chances, the probability to generate a data point X. And we've generated a bunch of data, so we could try to maximize the probability of generating the data. So pick the parameters to maximize the probability to generate the data, which is your x1, x2 up to xn. So to maximize the probability to generate your data, this is the method of maximum likelihood. Okay, and indeed, the method of maximum likelihood. Okay, and indeed you can set up the likelihood and go ahead and try to maximize that iteratively using gradient descent. There are many local minima and so on and so forth, but you can do that. Okay. Now what I'm going to describe for you is a very nice, elegant algorithm. It results from an expectation maximization approach, and it is another example of an alternating algorithm. We already saw one for K-means. So we'll continue that theme, and I'll show you another alternating algorithm. It is an expectation maximization algorithm. Okay. And you can see all the details and sort of the rigorous derivation of this algorithm in the E appendix, okay, associated with this E chapter.